Hi, this is Amanda Kocher, and I will be talking about the neuromuscular junction today. So I just want to start with kind of a brief overview, and then we'll look at some of this a little bit more on the next slide. But the neuromuscular junction is the synapse between a motor neuron and a muscle fiber specifically. Several terminals of the motor neuron are going to activate several muscle fibers all at once. And so when we look at the neuromuscular junction, though, we're just looking at one incidence of what contraction is going to result from that nerve impulse. Acetylcholine is the neurotransmitter that is involved with the neuromuscular junction in order for muscles to contract. And one of the kind of things specific to the neuromuscular junction as opposed to synapses between neurons, for example, is that the postsynaptic membrane is always going to be excitable. There's not an inhibitory response for that postsynaptic membrane. The neuromuscular junction involves both voltage-gated and ligand-gated channels in order for the process to work, and later we'll kind of talk about why that is a good thing, but also some of the things that can go wrong with that. And then finally, acetylcholinesterase is the enzyme that is going to actually break down that acetylcholine to end muscle contraction so that our muscles can make one kind of fluid motion and then go back to their resting position. So on kind of that big picture scale, like I said, we have the spinal cord up here. We had our afferent and efferent neurons. Our afferent or sensory neurons are what are going to sense our stimulus, take it to the spinal cord. And then our efferent or efferent neurons are our motor neurons. And they're what's going to actually take that back to the muscle, take that nerve impulse back to the muscle, and then meet that neuromuscular junction. And that is really important to keep in mind as we kind of move through the nervous system, move through the muscular system, and how all of this works together to make our bodies work. Nice, fluid, coordinated motion. All of this kind of has to happen in the order that it happens in, and it has to happen efficiently. So let's break down the neuromuscular junction a bit. And this picture always looks really busy, so it's one that you kind of have to spend a little time with, looking at, breaking down, figuring out what the arrows mean, what each of the gates are, what kind of gate they are, so that you can really work through this process. So it starts with that action potential that is going to come down the axon of the motor neuron so that it can get to the axon terminal. That terminal button is where we see all of this in here. And on the outside, on the membrane of this terminal button, we have these calcium channels. Now the calcium channels are voltage-gated channels. So as that action potential propagates down the motor neuron, it's what's going to actually activate those calcium channels to open. And when those calcium channels open, there's an influx of calcium into that terminal button of the axon. And this influx of calcium is going to stimulate vesicles that are carrying the acetylcholine, which is that neurotransmitter that I mentioned on the last slide, carrying that acetylcholine, and it is going to, those are going to move and merge with the membrane, and exocytosis will occur, pushing that acetylcholine, all these red little dots, out of the axon terminal and into the synapse. Okay, so we have this synapse, this gap between the terminal button of our axon and in the pink our muscle fiber down here. Okay, and what you'll see on the other side of our synapse is we have all of these acetylcholine gated receptors, and these receptors are ligand gated. They're those chemically gated receptors. So you remember we have voltage gated, and then we also have chemically gated or ligand gated channels that are important in the neuromuscular junction. So those ACH bind to those specific receptors that are meant for them. That neurotransmitter, it's like lock and key. That neurotransmitter binds to the receptor and the receptor opens. And these receptors, or these channels, are not cation specific. So sodium can flow, potassium can flow. But there's going to be a much greater influx of sodium into the muscle fiber, which you see with these arrows here. Our black arrow is a little bit thicker, noting that that sodium is flowing in much faster than the potassium is flowing out of that muscle fiber, which is going to ultimately cause an end plate potential. Okay, so if we look at this next, just so that we have a little more direction here. So it's going to slightly depolarize this part of our muscle fiber, and as it depolarizes that creates this end plate potential, and that end plate potential is going to stimulate a local flow of current. And that local flow of current, which we see over here, is going to open more voltage-gated sodium channels, which should sound familiar as kind of the start of propagating an action potential across a membrane. So as the sodium influx depolarizes that muscle cell further, then now we have the ability to propagate that action potential further so that then it can stimulate those sarcomeres to contract ultimately. Once our muscle has contracted and that nerve impulse stops and the brain is saying stop contracting, then that acetylcholine esterase, which is found here in blue, these little blue spots that are just kind of hanging out there, they're going to break down any acetylcholine that is just floating around here in the synapse. And as it breaks it down, then that muscle contraction will stop because there's no longer the acetylcholine opening those ligand-gated channels. Therefore, it stops the flow, the influx of sodium. Therefore, it stops the voltage-gated channels for sodium being opened, and now our muscle can relax. So this is great. It's a great process. It's an efficient process so that we can have this rapid muscle contraction that's coordinated. But as you notice, there's a lot of receptors that go into it. There's a lot of little pieces that have to fall in place at the right time and in the right order in order for coordinated muscle movement to occur. So what happens when this goes wrong? Okay, so that's what I always come back to. We always talk about this in anatomy and physiology. Like, yes, it's great to know how it works, but also what happens when something goes wrong. So one of the challenges with the neuromuscular junction and its complexity is it has a lot of different vulnerabilities. It has a lot of points at which things have to happen correctly, or paralysis could occur, or which is prolonged muscle contraction. Or maybe you have the opposite of that, where you don't have muscle contraction because you're not able to get those signals across. So I put 3 on here. The venom of a black widow, part of its challenge is that it causes this massive release of ACH from that axon terminal. And this ultimately causes prolonged contraction and paralysis, which is paralysis. The botulinum toxin does the opposite. It completely inhibits the acetylcholine neurotransmitter from doing its job and causes no muscle contraction, which kind of is a little different kind of paralysis, in that your muscles can't actually contract, so they're in this prolonged state of relaxation. And then myasthenias gravis inactivates the receptor channels, those ligand-gated channels that ACH binds to on that postsynaptic membrane. And ultimately, this causes prolonged muscle weakness. And the reason this is it inactivates the acetylcholine receptor channels, and those neurotransmitters can't as quickly or efficiently activate or depolarize the cell membrane because certain receptors are not active, and therefore not as many of them are going to be open as that acetylcholine comes across the synapse. One of the things, like all three of these have different vulnerabilities from the neuromuscular junctions perspective, but one of the things that is common between all of them, and really common between most neuromuscular junction toxins or chemical problems that come into play, are that the respiratory system, our breathing system, relies on our diaphragm, which is a muscle, to contract and relax in a coordinated, regular movement in order for us to breathe. And so in these types of situations or these types of chemical challenges, the respiratory system is often what fails and ultimately causes these to be fatal interactions. So ultimately, we want our neuromuscular junctions, all of them, to be working properly. We want to make sure that we're protecting ourselves from any challenges to this process that we can, and just being aware of kind of how it works and what we come into contact with on our daily basis. Thank you so much for listening, and I hope you have a wonderful day. Thank you.